Hi everyone, this is Roland from graphicinmotion.com. Have you ever wondered whether modern AI can teach us a professional 3D software like Houdini? In this video, we are going to explore exactly that. There's been a lot of buzz in the 3D artist community over the last years whether AI will take over our jobs. And as a 3D artist and educator, I really hope that this will be never the case because I love my job and I love to share my knowledge with the community and I love to create tutorials. So how real is the threat of us content creators being also replaced by AI? That's what we are here to find out. We'll be running a little experiment today. I'm going to use the latest version of ChatGPT to guide me through two different effect setups in Houdini. But before we dive into this experiment, I have a little favor to ask. I run this YouTube channel since 13 years now, and I still did not reach my goal of getting 100,000 subscribers. So if you like my content, then please consider subscribing to my YouTube channel. And if you want to further support me, check out Patreon. There I have a lot of exclusive and premium content about Houdini. And now let's see whether AI can really teach us Houdini. Good, so I'm here in ChatGPT and I actually use the paid version, and the most recent version is ChatGPT 4.0, and that's what we're going to use now. And I will just copy my prompt in that I already created. So let's paste it in here and let me read this out to you. I will tell ChatGPT, act as a trainer for SideFX Houdini. I want to learn Houdini and I am a beginner. Write a step-by-step guide how to create the following effect. Cover a 3D object with many spheres. Scale and colorize the spheres using a noise. Animate the noise to change the effect over time. I don't need any camera, lights and rendering, just focus on the effect. And now we'll just send this over and let him create the step-by-step guide. Okay, so it's done. Let's take a look at the result. And you see that he created a really nicely structured instruction. So we have each step outlined here. Everything is with bullet points and so on. There's also some VEX code in here. So we will use some attribute wrangles, as I can see here. And yeah, this looks pretty promising. So let's jump into Houdini and let's actually try to build this. So now I'm on the object level and let's see what our step number 1 is. It is setting up a 3D object, create a geometry node. So we have to create a geometry node. He doesn't tell us how to do that, but yeah, I know how to do that. I press tab and then add a geometry node. I already had some results that actually really told me each step. So press tab and write geo and all that stuff. This is obviously not that detailed. So let's see. Import or create a 3D object. Inside the geometry node, either create a basic shape, sphere, box, or whatever. For this example, let's use a sphere. Okay, let's use a sphere. So let's just enter this geometry node and add in a sphere. And connect it to the output. So I think that in older versions of Houdini, something like an output was actually a part of the sub network. Right now it is not. So it's possible that he's referring to an older version of Houdini, but I'm not sure because I'm using Houdini since I think 3 years now, and there never was an output node necessary in a geometry container. Now, cover the object with spheres. Append a scatter node to the sphere node. So let's do that, a scatter node. Okay, so we have some points scattered on our sphere. Adjust the scatter node parameters and control the number of points. For example, the force total account. So if I press P here to reveal my parameters, then I have the force total count and I can change that now. But I will leave it at 1000 for now. That's fine. Now, copy sphere to points. Create a sphere node that will be copied to each point. Adjust its radius to a small size. So let's just duplicate this sphere actually. And let's adjust this to a small size. So we say something like 0.05. Let's see, that's small. Maybe we go even smaller, something like that. Use a copy to points node and copy the small sphere to each scattered point. So we'll do this, copy to points. connect the sphere node to the left input and the scatter to the right. Okay, sphere node to the left, scatter to the right. Let's take a look. And you see this works fine. Now, scale and colorize the sphere using a noise. Add an attribute wrangle for noise scaling. Append an attribute wrangle node after the scatter node, but before the copy to points. Okay, let's do that. So attribute wrangle. And use the following Vex code. Let's just copy this over. We can just click here on copy code and paste it in here. And you see that he's just creating, actually a noise, and it's P times 10 plus time times 0.5, very interesting. And then he is just creating a range between 0.1 and 1 and adding this to the P scale. So is this now already animating? Let's take a look. Yeah, it actually is, as you can see here, because he put in this add time variable here. So that's pretty cool. But what I will do with my sphere, I'll make it a little bit bigger. I think it is too small. Yeah, this looks nice. So not that bad, actually. Already quite nice. So here's our attribute wrangle. And let me quickly rename this and say that this is randomize p-scale. Okay, so that I don't get lost. And he tells us this code uses a 3D noise function based on the position and time to generate a scale factor for each point. The fit function remaps the noise values from 0 to 1 to a desired range of 0 to 1 to 1.0. That's really cool. So he explains what he's doing here. That's really good. Now, add an attribute wrangle for colorizing the noise. Yeah, append another attribute wrangle after the previous one. Okay, so another attribute wrangle. That will be our color. Let's rename this to color. Use the following Vex code. Let's copy this in again and paste it in. And now let's see what we got here. So you see that we have colors and they're actually also changing over time. That's pretty cool. So he now basically uses the same code here just to affect the color, which is really cool. And then he's again explaining it, you know. The noise functions in the attribute wrangle already include a time component. Yeah, the add time here, that's this one here. This makes the noise change over time, creating an animated effect. Now, final adjustments and viewing. Adjust parameters. Fine-tune parameters in the scatter node, copy the points, and attribute wrangle to get the desired density, scale, and color variation. Preview the animation, go to the timeline, and hit play to see the spheres changing scale over time. That's it, you know. And yeah, I have to be honest, and I think that the result is actually pretty cool. If you take a look at that here. So yeah, now we could come in here and, for example, just use more spheres here and scale down the size again. Let's take a look. And we can also set this to pack an instance, because then it should run a little bit faster. Maybe go even smaller here. That was a little bit too small. Something like that. Yeah, that looks pretty cool, you know. And now you see we have this really cool result. Yeah, ChatGPT, actually that was not too bad. Pretty good. Now let's check out the second example. Okay, so I'm ready for the second example, and I just started a new ChatGPT chat here, and I will enter my prompt. And the prompt is pretty similar as the other one. Again, I start with this introduction, act as a trainer for SideFX Houdini. I want to learn Houdini, I'm a beginner. Actually, I misspelled this, I just see. So maybe this makes a difference now. Write a step-by-step guide how to create the following effect. Create a balloon inflation using Vellum. I want to inflate a sphere. In the beginning, the sphere should fall on the ground like an empty balloon. Over time, it should inflate and rise up. And again, I add this in that we don't need any camera lights and rendering and stuff. Now let's create this and let's see what it will come up with. Okay, so it is finished. And again, he creates this nice structure with all the bullet points and each step explained. Let's quickly take a look at that. So We will create a balloon node, and then he starts to add a sphere, polygon, frequency. That's fine. Add vellum configure cloth, constraints for inflation. Okay, that makes sense. Yeah, let's just run through this and let's try it out. So go to the object level. I'm here, and I will create a new geometry node and call this my balloon. So you see, I still have my setup from the example before in here. I can just turn this off for now. And then I enter this. Dive inside the balloon node, create a sphere. So let's create a sphere. And in this sphere now, set the primitive type to polygon and increase the frequency to 40, like so that we have a higher resolution that makes sense. Now attach a vellum configure cloth. Okay, vellum configure cloth. So it's obviously not aware that there is actually a configure balloon setup that would create two of these constraints for us. But yeah, let's see how this works. And we attach it to the sphere. That's what I did here. Now we need to add in constraints for the inflation, and he wants us to create a constraint type of pressure. That's fine. So constraints, and we link these up here and change the type to pressure. Okay. Adjust the wrestling scale and the pressure values to control the inflation. You can start with a pressure value around 1. Yeah, the thing is that there is no such thing as a pressure value. There's only the wrestling scale. And if you know, then this wrestling scale is actually controlling the pressure, you know? So that's a bit misleading here, but okay, right now everything is fine. Now set up the vellum solver, add a ground plane. That's what we will do here. So add a grid. Okay, great. And transform it so that it acts as a ground plane. Position it just below the sphere. Okay, let's do that. So we'll just go in here and position this ground plane and our sphere, something like that. Let's turn off this grid. Okay. Now create a vellum solver. Connect the output of the vellum constraints node to the first input of the vellum solver. So let's connect this up here, and let's actually make sure that our time indicator is on frame 0 here, or on frame 1. Good. Now connect the grid to the collision geometry input. Yeah, the collision geometry input is the third one here. That's fine. And he says that we should connect it to the vellum solver. So yeah, that's actually okay. We could do it like that. And because we follow every step that he is telling us, I will do it exactly like that. No? Now, animates the inflation, animates the pressure attribute. Go to the vellum constraints node where you set up the pressure. That's this one here. Set the initial frame to a low value of 0.1 and start to deflate. Well, the problem is now, where do we set this keyframe? He does not tell us this. And the second problem is it's actually not possible to animate these values because vellum will not take this into account. So this is misleading and will definitely not work. So right now I cannot figure out how to do that. And if I know my way around Houdini a little bit, I realize that there is definitely a mistake here. What we will do now is to tell this ChatGPT. So I will say that under point number 4, animate the pressure, that this is not working. So let's say under point number 4, the pressure animation is not working. There is no pressure parameter to animate. So please find a better method how to animate the inflation. Let's say the vellum inflation. Maybe this helps him. You know, the vellum inflation, vellum balloon inflation over time. Let's see whether this will get us to some results that will work. Now he will probably just recreate this whole thing. Yeah, that's what I was expecting. And he will just change point number 4. And I know I tried this out already, and I know that it has actually big problems with doing this, because usually you have to go inside the solver and do these changes in there. And yeah, let's see whether we can get it to work. So now he updated this, and now he say, inside the Vellum constraints node, there is no direct pressure parameter that can be animated through keyframes. Instead, we can use a point wrangle to manipulate the pressure attribute over time. Okay, now it gets really interesting. So let's see what we have here. He wants us to add a point wrangle before the Vellum solver. A point wrangle before the Vellum solver. Okay, now let's try it out. What he wants us to do. Connect the output of the Vellum constraints node to the input of the point wrangle. Yeah, let's do that. Okay, like so. Now, of course, we have to import this to the solver. He did not tell us this, but let's do it. And now let's add the following code. So let's copy this code to our solver. Let's see what he does here. So he's actually creating a scale variable and fitting this, depending on the time, from frame 1 to frame 100 for a value from 0.1 to 1. And he sets this as a rest length, or he multiplies the rest length attribute with this scale value. Okay, this is good, but what will happen now? This code will linearly interpolate the rest length. Yeah, that's true. Now, as the balloon inflates, we need it to rise. This can be done by controlling its buoyancy. Oh, now it gets very interesting. Add a pop force node to the forces input of the Vellum solver. Well, right now, there is actually no input for forces on the Vellum solver. If you don't know that you can dive inside here and find this here, I again would be lost. I want to tell this ChatGPT. So under, which number is it? 4.2, yeah. Under point number 4.2, there is no forces input on the Vellum solver node. Where can I put the pop force node? Let's see whether he can actually answer this question. And now he changes this one again. So the point wrangle, that's the same here. This is also the same, okay. And now we have this here. To apply forces, we'll use a dot network, create a dot network on the object level. Oh, now it gets really complicated and probably too confusing. Okay, but anyway, we'll give it a try. So what does he want us to do? To apply forces, we'll use a dot network. Create a dot network node at the object level. I'm in the geometry level. Okay, let's do it. Object level dot network. Why not? I think he's up to something. Okay. Then dive into the dot network. Okay. Now add a Vellum object. Okay. And point it to the Vellum subpath from your balloon geometry. Okay, so let's check out how we can do that. How can we point this to, there's initial geometry and initial constraints. So probably I have to point this to the Vellum subpath of my geometry node. Well, I have no idea how to do that. He says, add a Vellum source node over, like, maybe this is the solution. Add a Vellum source node, set it to existing object. Okay, so let's do that. No. Bindings, source, existing object. There is actually absolutely nothing. There is a subpath, constraint subpath. Okay, so I don't know how to do that, Add a pop force node and connect it to the force input of the Vellum object. Well, Vellum object, there is no force input. Set the amplitude. Okay, so sorry, but this definitely does not work. So we are somehow completely lost here. I will give him one more chance, and then tell him that this number 4.2 absolutely does not work. Under number 4.2, or let's say it like this, the instructions under number 4.2 do not work at all. Please find a solution without creating an additional network. Let's see whether this helps him. Probably not, but we'll give him one last chance here. So let's see what he will do now. Oh, and actually I made a mistake here. I told him, please find, that could be a problem. Let's see. What did he say? I apologize for the confusion. Let's go through the correct method. Okay, he understood what I want. So again, he has this thing with the point wrangle. Now he creates a pressure value here in the vellum constraint node. Okay, now he does this completely different. And then what does he do here? Yeah, okay, this will also not work because I know that this will not work, but we can still try it out, you know. So let's go in here, let's delete this dot network, let's go to the balloon here. And inside the vellum constraints node, we need to create a dynamic pressure attribute that can be animated over time. Connect the output of the sphere node to the input of a point wrangle. Yeah, okay, so let's do that, you know, point wrangle. And let's delete this one here because I think that we do not need this anymore. Now in this point wrangle, we copy this vex code here and let's see what he's doing here. He's actually again creating a pressure attribute and fits this over time for the first 100 frames from 0 to 1 to 1. So he created this linear interpolation again, that's fine. And now he wants us to use this pressure attribute in the vellum constraints node under pressure tab. So that's again this problem because there actually is no such thing as a pressure tab, you know. And he wants us to change the pressure field to use the custom attribute and set it to add pressure. That definitely does not work because there is no such thing. The only thing that I could do is put it into the rest length scale, but this will also not work. So we can just put this in here. And now this is somehow linked to this attribute that we create here. As you can see, we have this attribute here. But anyway, it will not work, you know. Now he wants us to add forces to make it rising. This can be done inside the vellum solver. So now he solved this actually, you know, because this is true. We can now dive into the vellum solver, add in a pop force. So this part here now may really work and connect this into the force, you know. Add a pop force node, set the amplitude to a small positive value to simulate the rising effect. Well, actually, if we set this to a small positive value, this will not create a rising effect. But okay, that's what he is telling us to do. And now we can see whether anything is happening here. So run the simulation, go to the solver and play the timeline to see your simulation. So now I'm really excited and see what is happening here. And this probably, yeah, it's shrinking down because we actually get this attribute into our pressure constraint. So this was actually working. Now we have a rest length scale here of 0.1. But the problem is that it will not take the change over time into account because these constraint nodes just don't do that. And you usually have to go into the vellum solver, add a constraint properties node and animate the rest length scale there. And that's where ChatGPT just loses. You know, it just is not able to create these more complex setups. And yeah, that's more or less it for this little experiment. I will let this calculate a little bit more. Okay, so now we calculated this simulation about 136 frames. Let's take a look at the result. And it is actually just shrinking down and then falling to the ground. So to do this properly, let me show you this. Let's get rid of our attribute wrangle. Let's get rid of this here. So just delete the channels here and set the rest length scale to 1. And usually what you want to do is, we can also delete this pop force or make it inactive for a moment. You want to use vellum constraint properties node here. And you want to make sure that this runs over the right group. which we have to create here. So let's set this to group pressure and make sure that this is spelled correctly so that we can find it. Then go in here and set this to group pressure. And now we can just animate the rest scale here. So now we just do the same thing that he told us. We will create a linear animation here, setting a keyframe 0.1 on frame number 1. I will turn off the calculation here for a moment. And I will just move to frame 100 here and set a keyframe to 1. And this was exactly what he was trying to do, but he didn't do it in the right way. And to actually make this rise, we would have to do something like this. We would have to animate this force value here to a positive value. So we could set this up, let's say in the first 24 frames, it should be 0. And then we could slightly increase this to maybe a value of 1.2, 1.5, whatever. And yeah, we can leave this amplitude in here. This will just add a little bit of turbulence. And this should now be fine. If we run this simulation, we should actually get what we expect. The only thing that we can change is to make this maybe a little bit softer, set this bend stiffness, or harder actually, because this is very low, set the bend stiffness to a value of 0.01. That's all that I would change. Maybe change the density here a little bit, but yeah, actually I don't care about this too much now. So let's see what this will do now. This is my improved result here. So this is the result that I get now, and you see it falls down and starts to inflate, so it nearly works. The only problem that we have is that actually under the solver, under the forces, we still have this gravity that is working against our force inside the solver. So we should set this maybe to a value of only -1 and then go inside here and change our strength here a little bit. So instead of setting this to 1.1, we set it to 2.5, let's say, and create a new keyframe here. And now this should work as expected. And I will just calculate this again, and I will be back when this is done. Good, so our simulation actually calculated, and of course, it's not perfect, but at least something is happening and it's working a little bit. We would have to spend more time here refining these keyframes, adding more collision passes here, maybe more sub-steps, refining the settings of the vellum cloth and the vellum pressure. But that's actually not the point here, and I don't want to waste your time. If you want to learn this effect, then I will blend in a link to a tutorial now that I created where you can really learn how to create controlled inflations. But yeah, that's the end of this little experiment. Okay, so that's it with this little experiment, and the outcome is that AI is fortunately not ready yet to replace us 3D artists and tutorial creators. You saw that it does quite a good job with a simple setup, but it had its problems when it gets more complex. It was not able to correct its mistakes, even if I pointed them out to it. So I hope that I still have a few more years left as a content creator, creating tutorials for you guys. I thank you very much for your support, and I really hope to see you soon. Goodbye.